live for the NorthSec, we have people live from my platform, and we have people on site. So we have people all over the place, literally, and probably all over the world. Um, Let me just start the recording for the people online on my platform. Just a shameless plug, by the way. I do a recording session like that all the time. This is part of my platform called truecyber.world. So I do these usually twice a month. It's pretty much the format that you're going to see today. I just wanted to give it a try in person too, because I thought it could be cool to also have a on-site crowd for that. So yeah. We'll get the recording started and we'll get going. Hmm. Okay. Good morning, everyone. Today is a special one. We have people on site, we have people live from the NorthSec, and we have people live from my platform. So that's the first from one. For me, hopefully everything's going to be totally fine. For those of you that are familiar with the platform, what I do is I hate myself for 2 hours while coding live in front of you. So if I do some mistakes, you're going to have the pleasure to enjoy them live and see me struggle trying to figure out what's the issue with the code. For the people online, they're used to it. It's just that they don't see me struggling. So that's that. The purpose of this is for those of you that actually attended my talk yesterday, I demonstrated what I believe is a novel technique to get shellcode execution within a .NET binary. Of course, we have 30 minutes, so it kind of flies super fast. So I kind of give you a quick overview of what's happening. The goal today is actually to write the code herself and also add the extra layer of fetching the shellcode on the server, make sure it's properly obfuscated and all of that. So it's going to be a way more complete version of what we saw yesterday. And if you want to actually give it a try on your side, feel free to do it. What I'm going to use is Visual Studio with C#. As I mentioned, I'm going to try to comment every line and make sure that we have a better understanding of what's happening. So that's the goal of today's session. Just a quick recap on what's going to be the purpose of that episode. There's this concept where if you want to run shellcode in .NET, you're usually going to allocate memory location with read-write executable permission, because you have to have those permission enabled to be able to get your shellcode running. Of course, it comes with downside in the sense that when you use those APIs, there's a good chance that you may be detected. And this is what you want to avoid from EDR. So I wanted to be creative and find a new way to do it. So that's pretty much what I ended up doing with this technique. I think it's fairly interesting, and this is what we're going to cover today. As I mentioned, you have a lot of things to take care of. Obviously, the shellcode itself, which is going to get you detected. Personally, I don't put the shellcode inside of the binary because I want to have the ability to change it if there's anything or make sure there's no detection on it. So the first part that we're going to do is actually fetch the shellcode remotely. To do so, what we're going to have to do is fairly simple. Sorry, I'm having issue with the mic. I'm just trying to figure out how to talk and write code at the same time. So please bear with me. So first things first, we need to create a piece of code that will fetch your shellcode remotely. We'll take care of the server later on, but for now, what we're going to do is we're going to create a little method that allow you to get to an URL and fetch the code. And I'll explain to you why I use some pieces of code versus others. There's reason behind it. The first things, you may be familiar with C#. Just out of curiosity in the room, by raising your hand, anyone familiar with C# who has written C# in the past? Okay, so I'd say probably a 3/4 of the room. You are probably familiar with the JSON format. Historically, for whatever reason, Microsoft didn't want it to support JSON. Not sure why, but the latest version does. You will realize soon that I don't use the latest version. The reason is fairly simple. You want your code to run on pretty much every system, right? So they may have not installed the latest version of JSON. I'm fully aware that natively now you can use the JSON library, but in this case, I'm going to use the terrible JavaScript serializer one just because it's actually supported by .NET 4. And that's the reason why I'm using that one. So I guess we'll get started. What we're going to do here is create a method called, I guess, get API data. doesn't really matter. Of course, if you want to create your code afterward, you can actually obfuscate it. Here, I'm using the T type. It's just mean that, hey, we're going to return something with a specific type, and we'll come back to that later. But the T is going to be actually a specific method that we're going to define that have a specific structure. And of course, to get to that, we need an actual string. So we're going to pass a string as a parameter. Nothing too fancy here. Because we're going to do web and you don't want your payload to crash, let's just surround the rest of the code with a little try catch, because we want to make sure that if it crash, well, we can actually take care of it. What you can do in your catch here, if you're really interested, you can actually show the exception. It's really up to you. Personally, because I know that I'm going to run this in a context where I probably have zero visibility, you could literally ignore it. But for debugging purposes, you probably want to show it. The idea here is that you can just have the right line. So with the message, so if for whatever reason, let's say the URL is not valid anymore or something like that, you're going to get the error, or your JSON is malformed or something like that. So it's important, but in production, I will probably get rid of that exception handler. So first things first, we need to do some web. The cool thing about language like .NET, it's fairly easy to actually issue a web request. In this case, what we're going to use is the web request API that allow you to actually create a request where we're going to pass the URL. The cool thing too is there's this concept of casting structures to other structure. Web requests support a bunch of methods, but we're going to actually force this to be casted as an HTTP web request. The reason why we want to do that is we want to have more access to more interesting functionality that we can use with that structure. So here's the thing. Now we're going to actually create the actual variable. So HTTP web requests. Usually when I create project like that, I like to call my variable in a simple way. I usually use the camel case because that's what .NET use. So I'll use the first letter of each camel case. So HWR. So I have a variable name HWR. It's not necessarily that convenient, but at the end of the day, you're usually going to use that code and create something that will make it even uglier later on. So the truth is, it doesn't really matter how you call it. Personally, it works for me. So at this point now, what we're going to have is a instance HTTP web request that contain whatever data was processed by the request. So we obviously need to actually capture that information, and this is where we're going to do here. So we're going to use a stream reader, which allow you to read a stream of data. Nothing super fancy here. What we're going to do is ask that stream reader to actually read the response that we got. In this case here, the response is part of the original object. So inside of the HWR, you have this thing called get response stream. So use the framework to your own advantage and actually get the information from there. Sorry about that. Let's just change something just to simplify stuff. Instead of using a request, we're going to use a response here right away. And what we're going to do here is leverage the oriented object concept, and we're going to save just an extra line because, you know, it's all about making the code as simple as possible. So we're going to get the response here. Oops. So in this case here, we asked for that, and I'm just going to cast this back to a web response instead, because we don't need the request in the sense that we don't have to add anything to it. So let's actually keep it simple. So HTTP web response, here we go. And the get response actually return a web response that we casted back to an HTTP web response. And what we're going to do here with that object, and funny enough, it doesn't change the name of the variable because of how it was actually created. And we're going to get the get response stream. So at this point here, what we're asking is to get the stream of data associated with the response. So we have whatever it's inside of it. So now inside of this, what we're going to do is get the actual data out of this. And notice here that I'm missing the new in front of the stream reader. So now we have this context where we actually get the data. And this is where we're actually going to fetch the JSON. The idea is this is pretty much what I presented during the talk yesterday. I think I use XML, but in this case, we're going to use JSON. So the idea here is that we're going to assume that we're going to get JSON data. So we're going to create a JSON variable. And we're going to ask the reader, I guess we'll call it reader, to collect all the data. So please read until you reach the end and store whatever you got in there inside of the JSON variable. At this point now, what we have is the JSON data that we are looking for, and I'm missing a parenthesis here. Here we go. Now this is where it's going to get ugly on purpose. As I mentioned, you could use modern.NET to actually use the built-in the system text JSON or something slightly different, such as Newton JSON or all of these. Just know that if you want to use the external one, you can actually use IL merge to actually merge all the code in one single binary. Of course, when it comes to malware, you want to have the simplest binary as possible. You don't want to have to ship any kind of dependency or none of that. So now we're going to extract the JavaScript, the JSON, sorry. And we're going to use this terrible JavaScript serializer method, which is built in .NET 4. Notice here that it doesn't even know what it is. If you show potential fix, it's going to tell you that, hey, you probably want to use system web script serialization. So you'll be like, yes, please. That's exactly what I want to do. So now it took care of actually adding the dependency. So we're using built-in capability, purely based out of the name. This has probably nothing to do with JSON, but for some reason, it kind of does. So let's call this serializer. And in this case here, what we're going to do is just create a new serializer. Without any parameters, we're just going to use the default setting. So we're going to come back to T, which is just a generic type that is not defined. So it's like a nameless type, and we're going to define it later on. The idea here is that you can keep your code as generic as possible. So if you want to change that structure in the future, you'll be able to. So we're going to have a result here, and we're going to use the serializer, and we're going to serialize this as T. So we want the JSON to be serialized into that result. So what's happening here under the hood is that you're going to end up with a JSON object. The thing with JSON is that it's a super easy web format. It makes sense if you look at an application perspective. If you've done a bit of web app testing or you enjoy web, you'll notice that pretty much nowadays everything is JSON based. When it comes to malware, the idea is to actually blend in as much as you can, right? So this is exactly what we're going to try and achieve here and make sure that we look as normal as possible. Once we have that data here, what we're going to do is simply return the result. If in a case where, for whatever reason, it fails, you want to make sure that your code is still running, we're going to actually return default T. So in this case here, it's just going to return the default value of T. So it's not going to be a null object, so at least your code is not going to crash. But keep in mind that if you reach that point in your code, there's a good chance that nothing's going to work afterward because you probably didn't capture the shellcode. So now, if you look at your code in your main, eventually what you're going to do is fairly simple. You're going to actually ask for the shellcode to be loaded within your program. Now we need to actually have a server side to that story, right? So this is where we're going to start using one of my favorite language. A lot of people don't like it, but I personally really like it. And it's called PHP. Any PHP fan in the room? That makes me sad. Literally no. Oh, one. Appreciate it. Thank you. Long time ago. But honestly, I believe that PHP is like C. It's a simple language. A lot of people complain about the fact that it's insecure like C because it allows you to do pretty much everything you want, right? So you just have to kind of take care of the security on your own. So this is where we're going to actually use PHP to simply write the server side because from my perspective, it's simple, it's efficient, and it actually does the work. So what we're going to do here is also use my favorite editor, which is Nano, because I've never understood how Vim work or VI or whatever they want to call it. And I guess we're going to call this malware.php. So this is going to be the server part. For those of you that are not familiar with PHP, all you need in this case, for example, is install Apache and have PHP installed. Pretty straightforward. The reason why I'm using PHP, honestly, for most of my development when it comes to malware is because it's simple. No need to build like a massive framework or none of that. So it's always nice to have something efficient that can get you going in a limited amount of code. So the idea here is first, we're going to declare that we're going to return JSON because this is what we want to do. And this is exactly what the header function does. It allows you to set response header. So every time something's going to browse malware.php is going to add the header that says that, hey, content type is JSON, which makes sense in this case because we're planning to actually process JSON on the malware side. This is going to be an example here, so I'm going to declare data. We'll talk about it later, but let's assume in this case that this is our actual shellcode, so I'll call this evil string for now. What we want to do here is that we're going to create an array of actual data. Um, we're going to take each byte of your evil string. Yes, question? Yes, that's actually something in AWS. You could do it locally. Personally, I'm a huge fan of having a Linux subsystem on Windows. You can have all of that on your local system. You just install the feature, and then you have literally access to everything on a Ubuntu system or whatever distribution you decided. In this case here, I'm running it on a remote system, but yes, you could run it locally if you wanted to. There's even WAMP, I think it's called. It's Windows, Apache, MySQL, PHP. I'm not sure it's still around, but it does exist. But point is, yes, you can run it locally. It's just that in this case here, it's more convenient for me to run it on a remote system. Well, if you were to use this during a red team exercise, for example, obviously it's not going to work because you're probably going to put that payload on someone else's system, and it needs to be able to actually fetch the payload over something that is reachable like the internet, right? If you run it locally, nothing is going to happen literally. And in terms of EDR detection and or all of that, unfortunately, they're not going to pick that method, so it doesn't really matter in terms of detection. But yes, usually you want to have a virtual environment where you have no security projects to make the development more efficient. So back to this string. In this case, let's assume that this is the shellcode that we want to execute. What we have to do is actually create an array out of it because we're going to take all the bytes and we're going to shuffle them into an array. The idea is that the JSON structure usually look like something like that. In this case here, what we're going to do is we're going to create an item and we're going to have index, and let's say 0 is going to equals to what is it, E, for example, and then 1 equals to V and stuff like that. Of course, we want to make this as least static as possible, so we're going to shuffle the whole thing. But at the end of the day, this is the format that we want to create. We're going to have each byte associated with an index. Then we're going to shuffle this whole array. We're going to present it as JSON. And then on the other side, within the malware, we're going to rebuild that actual array. So what we're going to do is create this format using PHP. To do so, it's actually fairly simple. We're going to create an array variable, and we're going to specify that, hey, we want an array, and the length of the array is fairly predictable. It's always going to be the length of the data, right? We're converting the data into an array. So we're going to use a for loop. This is PHP, so we don't need to use any kind of fancy stuff. And the classic loop structure for a for, so we're going to say, hey, loop until you reach the end of the size of the data that you want to work with. So you end up with a simple for loop. And what we're going to do inside of that for loop is actually prepare the array with the information that we need. So remember, we declared an array variable, and we're going to use the index. The point of arrays that you can specify, hey, this array at index, in this case, 0, I want to put this information here. And what we're going to do is put another array inside of the array, because remember, the item is the array itself, and inside of the array, you have an array with an index and a value. So this is why we have an array inside of an array. And because it's PHP, you don't have to take care of the memory allocation. It's going to do it for you. So first information that you're going to store is the actual index. So in this case here, 0. And we're also going to store the value of the data at the index 0. So you end up with data of I within the array I at the location I within the original array. So now you actually have your data in that array. And this is where the fun began. PHP was kind enough to create a function called shuffle. So what you're going to do is you're literally going to shuffle the array. The idea is that you want to make sure that every time someone browses your page, the structure will be completely different, regardless of the fact that the original code is the same. So this is what you're going to end up with. And I guess just for the fun now, what we can do is have a var dump of that array. And this is something that I love to do because I always make typos. What you can do is literally simply ask your var dump to dump you the information. So malware.php. And as you can see here, we ended up with some data, right? So the first index says that the first one is an int, the value is 2, and it contains the information I. Remember, arrays usually start at the position 0. So 2 is actually the third character, which makes sense because the third letter is I in evil string. If we actually browse that page again, We refresh it. You'll notice now that the first one is index 1 with E, so this array is always shuffled like we expected. So it's nice because imagine that this was legitimate shellcode. All the bytes will be positioned in actual different location. This is exactly what we want. Different result every time you actually query it. Notice here that you also get a browser error regarding JSON. You get that error because the browser assumed that it's going to be valid JSON because you specified the content type as JSON. In this case here, we're just using var_dump, but we'll fix that later by actually doing something with this. So short term, this is what we need. The next part now is to actually build the valid JSON structure. So what we can do, we don't need that part to be generated dynamically. If we actually put 2 curly bracket, you'll notice now that the error is gone because this is considered to be valid JSON. It's just an empty JSON structure. So what we're going to do now is build the actual items in there. So this is where PHP is going to shine as a terrible language, but it's convenient. So we're going to use echo, which is basically print back to the server some structure. At least we're going to try to be a bit clean by using tabulation to make sure it looks like an actual answer. So now we're going to create the items, and we're going to specify that, hey, we want items to contain something, but we'll take care of that later. So now we have the beginning of that actual JSON structure. And at the end, you need to also close that one. So this is what we're going to do here. So if we run this, there's an error in my code. We get an error 500. Where is it? Yes, because I didn't close PHP here. Here we go. So if you run this here, you'll notice that we now have the beginning of the structure. We have the items and the 2 curly brackets. Inside of this is where we're going to have the array with all the bytes. And if you want to be fancy, just to look like you're an actual legitimate service, notice here that we could probably add a new line just to make sure that the curly bracket are positioned properly. So if we load back the page, you'll notice now that it looks like a legitimate application. So the only step remaining is to actually have the data that we have in the array. To do so, it's fairly simple. All we need is another loop. And I'm just going to separate this. Actually, I don't have to. We're going to create this output variable because we're going to append a lot of stuff to it. So we're going to start with each byte. Without much of a surprise, because we're going to work with each element of the array, we're going to end up with the exact same loop. And in this case here, we're going to specify that, hey, I want to get all the information associated with the size of the data. You could also use the size of the array. They're technically equivalent, but in this case, I rather keep the same structure because there's a saying that says do not repeat yourself. So we're going to do the exact opposite by repeating yourself in here. This is where we're going to build the output variable. This is probably the big chunk of it. Just notice that you can use double quote and single quotes. It's a bit annoying, but if you want to have strings as double quotes, you have to use single quotes. So we're going to start with single quotes. Inside of this, we're going to have double quotes. The reason why is because what we're trying to build here is a structure that looks like this. So one, because you need to have the double quotes to be valid JSON and whatever as double quotes. So we need to surround everything with double quotes to be valid JSON. So here we are. We have single quotes. Then, hey, we want to have the index. Remember, we created an array. So array of whatever index, in this case 0, and we want to have the first element of this array. Remember, first element is the actual position, and the second one is the data associated with it. So in this case here, I want index 0, which is the position of whatever codes we are looking for. Then we're going to create the other part of it, which is now the information. For a reason that I will explain later, instead of actually representing the letter as a letter, we're going to use the numerical representation. The reason why is when you deal with shellcode, most of the time it's going to be non-printable character. So you most likely want to use that actual structure instead to simplify your life. So we're going to use the function called ord, which will convert a char into the ordinal representation, aka numerical. And in this case here, we're going to ask for the array at index whatever. So in this case, I again. And instead of going for the first element, we're going to go for the second one. So we need to specify index 1. And now we just have to complete the actual structure by closing this double quote, adding a comma, and then we're done. So if I didn't make any mistakes, which is unlikely, we should be good to go. Of course, there's a typo. I always do typos. Here we go. There's a missing single quotes. I think we should be good. Oh yeah, that's right. Good catch. Funny thing though, if I run that code, it will have worked. PHP will have never complained about it. It will just assume that you created a new variable and there's nothing to see in there. So that's the kind of example where you may actually spend a lot of times debugging stuff. So if you actually load that page again, and apparently there's an extra problem, I will just save a bit of time by looking at the log. At least I will know what the error is. Dot equals on line 16. Oh yeah, here we go. Forget about the fact that I was actually doing PHP for a second. We'll just echo output here too so we can see it. And here we go. So we have this actual structure. So index 2, 73, 4, and as you can see here, they're randomly placed. Notice that there's a little problem. At the end, we have an extra trailing comma. Because if you look at the loop, well, every time we actually loop, we had a comma and a space. The simplest way when you deal with array like that is to actually just take care of it once you're done. What you can do here is use substring on the output. So when you're going to output the whole thing, you're going to start substringing the whole thing by removing the last two characters because you know that they're always going to be trailing. So the way that you can do it is you say, hey, I want to chunk this from index 0, and you're going to specify the length. And the way that you can specify the length is going for the whole size minus 2. So you're going to end up printing pretty much everything except the last comma. I have like 20 of those open. And as you can see now, it's actually rendering properly because we got rid of these two. So now we have 100% valid JSON. Just something interesting. Notice here that I actually show it in order. So it starts from 0 to 9. But the reality is that if you actually look at the code, they're not in order. It's just that the browser trying to art smart you and be like, hey, by the way, guys, why don't we put this in order? But the truth is the actual data rendered in the browser is not set that way because we are actually dealing with JSON. What is actually cool is that we can add extra information to it that is not necessarily relevant. So what we're going to do here, because we want to legitimate, like it's a legitimate service, we're going to add an extra piece. Let's say, I don't know, code. Usually you see that with API where it's going to specify an error code or something like that. Let's return a 200, meaning that everything was fine. So if we look at this again, now we have this element items with this, and we have a code 200. Fair enough. So this is valid JSON. We're pretty much good to go when it comes to the malware now. So we are capable of actually fetching this. So if we go back to the C#, we have this method here that allows us to go get that code. So we need to actually take care of it. One thing now that we need to address is the way that you serialize it. So when you deserialize, you have to specify a structure. To do so, what we're going to do is we're going to add an extra class here that we're going to call, let's say, API data. And what you have to do in your code is to actually match what you're going to receive from a server perspective. So one of them is going to be public int code, for example. Remember, we implemented this code field that has no purpose, but you want to reflect that in your actual structure. So now we have the code there, and we need to also have the items. So what we're going to do here is we're going to use the concept of dictionary in C#. The reason why is because if you look at this, this is going to be a dictionary of 2 index. So we're going to have 2 strings into each element. And in C#, this is represented by a dictionary structure. And you can specify the actual structure. In this case here, first element is a string, second is a string. So it knows that every element in the data is actually going to be a double string type of thing. So you can actually take care of this on your own. And we are good to go. So now in the main, what we have to do is literally just to actually fetch that code from the remote API. So let's create an API data variable. Let's call this data new get API data. We can now specify that, hey, by the way, the specific type for this is API data. So it knows to do the casting for you. And the URL in this case, we're going to hard code it, but I'll let you be creative when it comes to hiding that part and malware.php. At this point now we have this JSON format. Obviously, this is not going to get detected at shellcode at this point, which is totally fine, but we're still going to have to work with it later on. The next step is to actually start hiding the shellcode deobfuscation, if we can put it that way. What we're going to do here is create a variable that we're going to call a byte array, which is going to be shellcode. I'm going to put it as static because we're going to deal with static method here. Okay, first step, we need to actually initialize that one. The way to do so is fairly simple. If you actually use the program, and notice here that I'm using the program dot all of this, is because everything is actually static. I guess I can put it as public, doesn't really matter. But when you use the static keyword, and this is what C# used by default, you have to reference it with the full name. You could technically just put shellcode, but I think it's just a bit more convenient to type it that way. So now we're going to define that we want to have a new byte array. And you need to actually get the size. And the beauty of it is, remember, we're dealing with JSON. So now we have the data. Oops. I just realized I'm actually outside of the domain. Here we go. We actually have the data structure and we have the item. Remember, we actually defined that one here. And because it's a dictionary, we have access to even more information, one of them being count. Remember, the number of element that we have in that array is literally the number of byte that we have in the shellcode. So what we did here is basically ask C# to allocate the memory matching the size of the shellcode. Now we have to build the shellcode. This is the easy part, and this is something that I've said a lot of time live. Make sure that you are not trendy when it comes to the way that you do your shellcode. Don't use arc4, AS, and stuff like that. Keep it simple. What we're gonna have here is literally just a for each loop. That's it, nothing else. So we're going to use this key value pair, which is part of the built-in capability in C#. Long story short, is just another way of defining a dictionary where you are, when you're doing a for each, you have to once again specify the type to string. And then we're going to say that each item in, oops, I hate when it autocomplete to stuff that we don't want. Item in data the item. So go through all the items that you have in there, and we're going to actually assign that to the shellcode. The reason why we want to do it like that is because it's fairly simple, right? Remember, we know that each key value have two information, the index and the actual data. The index being the first one and the data being the other one. Because we convert this into key value, key is the index, value is the actual shellcode. So to get to the proper index, because they're going to come in a random order, we're going to ask the shellcode to figure out, hey, can you parse whatever you got as the key into an int? Because it's a number, it has to be an index. So item.key is where you're going to get the index of whatever it's at that location. And please, can you actually set this? Remember, we have string, but it has to be parsed. So we're going to use byte to convert it as byte. The reason why we're dealing with byte here is because shellcode is usually a bunch of bytes that are not necessarily humanly printable. So at this point here, you ended up with your shellcode being ready to be actually executed. The shellcode program now contains the clear version of your actual shellcode. And what we're going to do here as an exercise, we're going to actually use the thread class available in C#. And we're going to kindly ask the program to sleep for an insane amount of milliseconds. And we're going to run this. Eventually, it's going to show up. Here we go. Now it's sleeping probably for an insane amount of time, which is fine. The reason why I hid that sleep is because I'm going to use Task Manager. Forget how I call this. Hello, I guess. Where is hello? So, oh, here it is. And I'm going to do a memory dump of hello. I'm going to open the file location. And this is sanity check that you should do when you actually deal with, with malware creation. I'm just going to copy this on my desktop. I'm going to open XHD. I love this X editor personally, but feel free to use whatever you want. And what I'm going to do here is actually load this. So hello.dump. Remember, We know that the server has obfuscated a specific string, evil string. The reason why I picked that one is to actually show you this. What we're going to do is search for evil in this. So we're going to search all over the place, search all. And without much of a surprise, the memory dump showed that there's evil string in there, which makes sense, right? You rebuild your shellcode, you did all the thing, and we also confirmed that the code is obviously working. But there's an issue. If this is malware, it means that at this point, your shellcode is actually unclear in memory. That's something that you want to avoid. Of course, a lot of tools will tell you that, hey, we obfuscated the shellcode. The goal is to actually defeat static analysis in the sense that there's no trace of that shellcode within the program. However, in this case here, what's going to happen is that if there's any kind of memory analysis, which happen often with newly modern tools and newly type of EDR like XDR, NDR, EDR, well, you're going to get detected because assume that this is shellcode associated with a C2 such as Cobalt Strike or any of that. You have that shellcode in there. So there's a couple of solutions for that. One that I love is to once again leverage .NET feature. Um, just know that at this point in time, this memory has been unclear for about a couple of millisecond or a couple of CPU cycle. There's this cool thing called protected memory, which is built in Microsoft, and it relies on crypto. When you see crypto and malware, you know that it's going to be fun. And you can actually call protect. Um, Now what we're going to do is ask the shellcode itself to be encrypted because we don't need it yet. We have a couple of extra steps to do, and we can specify the memory scope. In this case here, we're going to specify same process, meaning that only this process can actually access that encrypted memory. This will achieve two things. It's going to encrypt it in memory, so if EDR somehow end up taking a look at your memory location, well, nothing is going to be in clear. And we can literally prove that by rehatting the sleep, and we're going to do the exact same thing. We're going to do another memory dump of the exact same process. So now we hit the sleep. Oh, sorry, someone's calling me. Uh, and actually, we're going to get an exception. It's going to complain because, you know, it's crypto, and crypto always have to have some specific structure. In this case here, we cannot even reach the sleep because C# pretty much crash on us. The reason why, if you actually look at the error message, it's telling you that it has to be a multiple of 16 bytes. Of course, the shellcode is of whatever length. So what we're going to have to do is create a padding method that allow you to actually pad the code. So regardless of whatever shellcode you receive, you're going to pad it. So let's add a new method inside of this. So it's going to be static int calculate padding. And we're going to specify a size in here. The way that you do it is actually fairly simple. We're going to return a padding value, which is equal 16 minus the size of modulus 16. That's how you actually calculate it. So long story short, it's going to take whatever the size is going to make sure that it can actually found what's the modulus of it, and it's going to reduce this to 16. So if there's, I don't know, let's say a string of 12 bytes, it's going to return the value 4. So you know that you have to add an extra 4 of padding in your code to be able to use the encryption API. Uh, just one sanity check. If padding equals 0, meaning that there's no more padding needed, let's return 0. In the other case, return whatever the value of padding is. And now what we're going to do is super simple. Instead of passing the count, because it's going to be an arbitrary value that is not necessarily multiple of 16, we're going to force the allocation to match that. So instead of using the size from there, we're going to create a variable that we're going to call size, which is going to be data items count plus calculate padding of the exact same value. I don't know why it had 2 layers of calculate padding here, but here it is. So now, instead of using that value, you're going to use size here. Notice something really important. The loop remained the same. So even if there's like 12 bytes and it ended up padding it to 16, the last 4 don't matter at all. We don't care about those bytes because they're not going to be used. Yes, question? Can you just speak a bit louder because I cannot hear you? Uh-huh. AWS, cloud, whatever makes you happy. Correct. Correct. So that's what you're going to run on your target system. So that's your victim malicious code pretty much. The shellcode is actually, in this case here, the string evil string. We'll replace it with something that makes sense at the end, but for now, the shellcode is actually evil string. This is what you want to hide. And the reason why you need to have that extra padding here is because we don't necessarily know the length of that actual shellcode. In this case, it may be a multiple of 16 or not, but in this case, uh, by adding the padding, we know for a fact that it's always going to match 16, so the program will not crash later on. Is on the victim. Yeah. C# on the victim, PHP on an attacker control server. Make sense? Perfect. So as I mentioned here, we change the allocation size, but the loop does not matter. So let's say in this case here, there's 4 of padding. We're just going to literally ignore these 4 bytes because we don't need them. So now if we run the program again, notice that so far we don't have any red in here and it's sleeping forever, which means that the encryption was successful because it's a multiplier of 16. So everybody is happy. We did a dump once more. And in this case here, we're going to take the dump, put it in here. We're going to replace the other one. And we're going to reload it here. As you can see, it changed a bit. And if you actually search for evil, it's not there anymore, which makes sense, right? Because the memory is encrypted, everybody is happy. So this is where the fun began. If you saw my talk yesterday, I kind of showed you that normally what you'll do is actually rely on pinvoke, dinvoke to get called to protect memory and stuff like that. In this case here, what we're going to do is we're going to literally misuse the framework. The idea is that you want to get the address of a method. Keep in mind that all of these are C# methods. So what I'm going to do here is I'm going to create one static function, I guess static public, because let's make it public, void, and let's call it dummy. And this one is just going to do console write line and be like, hello, my name is Charles. We'll come back to that later, but long story short, just for the fun, we'll call that one in the main two. So dummy is going to be loaded at the beginning. So nothing malicious right now. If you were to look at this from a malware analysis perspective, obviously don't name your endpoint malware.php, but it's fairly simple. It's just a loop processing JSON data. This is just a standard, type of web API method. This one here is a bit shadier. Of course, don't call it shellcode, but it can be just, an application trying to get some data that is considered to be privileged. That's why it's encrypted afterward. And we have this dummy function, which is literally just C#. And the beauty of this technique is that you can put literally whatever the hell you want in there. It doesn't matter. Now we're going to create the little helper that we need to make all this thing interesting. We're going to use a return type of in-pointer. In-pointer is just a pointer to whatever. So technically, there is no pointer in C#, but the reality is that you can always get address of thing, and this is exactly what we are looking for here. So we're going to call this get method address, and we're going to need to pass the method info structure, which is not defined right now. Always be lazy, use whatever Microsoft will command you to save time, but all it does, it actually tells the code to load all of these required library. And funny enough, you may realize that some of them are kind of grayed out. It just means that they're there by default, but they're not used. So if you want to keep your code smaller, you can just remove the ones that are grayed out, so you have a smaller footprints in terms of code. So let's follow the same structure, method info. We just use first letter of every camel case. And this is where the magic happened. The idea is that when you actually deal with a .NET application, you write C# code. When you actually compile the code, it gets converted into something called CIL, which is the opcode understood by the virtual environment, because the framework actually have this environment that will interpret that code. Eventually, the framework itself, because CIL code is not something that your processor can understand, then it has to be converted into assembly code, which is now understood by the rest of your computers. So the framework eventually have to do the conversion from C# to CIL to actual assembly. Shellcode is assembly. So you have to get to that assembly. And the cool thing here is that you can actually force .NET to do that step for you much faster than it should. And here's what we're going to do. We're going to use the runtime method handle, and we're going to specify that, hey, we want to get the handle of the method that we pass as an argument here. Um, at this point here, what we return is an endl. In Microsoft term, an endl is just a structure that point to a specific piece of information. In this case here, it's an endl to a method. In this case here, the method info is whatever we're gonna pick. And I guess we can probably sort that out right away. The method that we're actually gonna try to get the information from is going to be the one that we declared earlier. So let's get the method information by using method info. And to do so, we're going to use some built-in information. One of them is type of. So we want to have the type of the program. This is the actual program. Notice here that the class is actually named. So hey, we want to have information about programs. And what we're going to get out of this is the actual get method and from helper. So get method allow you to return information about a method. Guess what? We're going to try to get the information about the dummy one, because that's the one that we're going to play with later on. So please provide me with the dummy method information. There's a couple of other bind flags that you can set. Just know that there's this concept of private, public, and all of that. You can actually override those and force access to be changed. In this case here, what we're going to do is binding flags, specify that we want this method to be static. It's kind of you determining the signature. In this case here, if you're not sure what it is, just look at the actual method itself. It's static and public. So the other one that we're going to add is a binding flag that says that it's public. So it's capable of getting the proper signature to actually get to the actual method. So now we have the method info prepared. What we're going to do here is have the in-ptr ready with the address. So we just have to call get method address on that specific structure, and we're going to get the value out of it. So now this is where we're going to have another cool piece of information. This is literally the line that changed my life. Runtime sorry, helper. Runtime is usually a good keyword regarding the fact that you are going to work with something that is happening in real time. So when you have the whole .NET environment doing the work, you're running at the runtime. And you have this runtime helper that actually allow you to do something called prepared method, where you have to pass a handle as a parameters. So once you get to that point, it means that, hey, I want you to actually prepare that method for me at the runtime level. Not sure why .NET actually offer you this, but I'll definitely take it. The idea is that you now have your CIL code, and at runtime, you ask it to be prepared into assembly. So you actually started from CIL, and now you have an handle to assembly code. And this is what is interesting, right? Because if you look at it from a shellcode perspective, you now have that memory location ready for you, and you can actually override that one. And I guess I can probably just show it to you by looking at the actual presentation that I did yesterday. Just give me a sec. So just for your own knowledge, if you write C# like that, whatever function this is, it get converted into CL. And if you look at 037E, this is what gets converted to. And it also have its own like structure in terms of language. So you have load, the argument one, and all of that. So this is what the CIL look like. Obviously, if you're trying to run this at the CPU level, it's going to basically tell you that it doesn't know what it is. So it doesn't work. However, this has to be eventually converted into assembly that you can understand. And back to what I was saying too, if you have ever used C# to run shellcode, you probably saw something like that where you have the user virtual protect, which is a red flag. EDR will detect you right away, and the delegate function. So you kind of have to create a function pointer to jump to your code. So that's definitely some red flags. You also have all of these that are added into your import. So when you compile your binary, it has reference to all of these, and these are also extremely bad red flag. So back to this, as I mentioned during the talk, I was using XML. Today we ended up using JSON. Doesn't matter. Use whatever format makes you happy, really. And back to this method here. the prepare method is just going to create a prepare method for inclusion in a constrained execution region. And that's funny because the prepare is really the keyword here. It's not going to put it in there for you. You have to technically put it in that limited memory space, but because you don't want to actually put it in there, you're just going to prepare it. And remember, we have an handle that points to that actual memory location. And this is exactly what this piece of code here will do. So once we run it, in this case here, you'll notice that address point to whatever memory location. And because the runtime has to actually be able to write to it, because it's going to convert CIL into assembly, you have the right aspect. Because it has to read that, obviously, because it's going to potentially execute it right away, you have the read. And because it's going to execute it as shellcode, not as shellcode, but as instruction, you also get the execute. So you have exactly what we're looking for from a shellcode perspective, a rewrite execute section that was allocated by the .NET framework directly, so you don't have to do anything. And the address point to that location, so you can write to it. And that's the thing. If you take a look at this, you'll realize that what it points to is the actual assembly code. Notice here, for those of you that have a trained eye when it comes to .NET versus assembly, you'll notice now that we have push, move, push, sub, which are, Intel instruction here, which means that the CPU understand that. But this is the definition of do something after it was prepared and converted into assembly. So if you can actually modify that with your own code, you're pretty much good to go. So this is what we're going to do here. We're literally going to use that function to get the address. The only thing that we need to do now is to return the actual pointer to it. So we're going to return the get function pointer. So now get method address, return the pointer. So at this point, we have a pointer to a memory location that we have full control over. We have the data, which is the shellcode. At this point here, the shellcode is actually encrypted. We have the method that we're going to override, which is dummy, that doesn't do really anything interesting. The last remaining step is to actually make sure that the shellcode is sent to that location. And this is what we're going to do here. There's tons of way to do it. Honestly, you can just be as creative as you want. I'm going to use the unsafe keyword here just because it's funny, and I love using pointer in C#, even if you're not supposed to. But in this case here, if you use the keyword unsafe, it's going to tell you that you need to actually enable them, because .NET is like, hey, I don't trust you. You're sure that you want to do unsafe code? So you have to go in build and check the allow unsafe code. But we're hackers, so we're used to do unsafe stuff. So using the unsafe keyword made a lot of sense in here. As I mentioned, I love to work with pointers in C#, even if you're not supposed to. So let's actually create a byte pointer. Because you're in an unsafe state, you are actually allowed to do that in C#. So let's actually use a byte pointer. And what we're going to do is, remember, we have the address variable that points to the memory location that we want to deal with. So we're going to ask this to be converted into pointers. So now what we have is a raw type pointer that points to that memory location that you want to work with. We're going to create another loop because we love for loop, right? I think at this point you're getting pretty familiar with all of these. In this case here, as you can see, .NET wants to auto-complete this to size, but remember, we don't want to use size because we have padding at the end that will not do anything good for us. So instead of using that, what we're going to do is we're going to do something like copying the value that is matching the data item count, because the extra bytes at the end are literally not something that you need. And then we're going to have this loop here, and this is where we're going to do the magic. I guess at this point we've done it multiple times. We're just going to use the index on the array and actually assign the shellcode to it. So in this case here, we have program shellcode I and all of that. So now we have this super nice copy of shellcode into that location. Remember one thing though, at this point here, we ended up encrypting the shellcode. The idea is that you want to have the shellcode in clear in a short period of time as possible. So before we actually go into that loop, we have to actually unprotect it. So let's make sure that I get unprotected for, a couple of milliseconds too. Once we are done with that, this is where we're going to actually start executing the code. And you may be wondering how I get that shellcode executed. Remember, all we did is to overwrite what's inside of dummy because we changed it at runtime. Question? The dummy one? Yes. There's no official way to do it, what I recommend is extremely simple. Go online, pick whatever C sharp project you want, take a method in there that is fairly big and just copy it in there. And that's the thing, what's inside of dummy does not matter at all. But as long as it's big enough, you should be good. But for example, later on, we're going to use a calculator shellcode, which is fairly small. You don't need to have that big of a function. Usually what I'll do for a calculator shellcode is probably copy paste this 5 or 6 times, something like that. That will be more than enough. If you're dealing with like Cobalt Strike, for example, and the stageless payload that are about a megabyte, you're going to need a slightly bigger function. But something to keep in mind too, that is really important. When it comes to memory permission, Microsoft used the concept of page. Even if you ask for 1 byte in a memory location to be rewrite executable, it's going to actually modify the whole page. And you can actually see it here. Use a tool that allow you to inspect process memory. And you'll notice that it tells you that the type is private data because Microsoft tagged all those regions. And it actually says that the size of it is 4K. So you have a 4,000 bytes that are actually set to execute rewrite. So usually you're going to have way more than enough regardless of the size of the. Was that? Correct, correct. So by default, even if you ask for 1 byte, you're gonna get 4K of it. But depending on where you're located in that page, it may change a bit, right? That's why you probably still want to have enough code in there to be able to actually have enough shellcode. But yeah, just make your method bigger if you need more space, literally. Correct. Well, yeah, it could be it, but the truth is the way that the .NET will actually handle the string, it's not going to be even stored in there. It's just referencing to another part of it. Yes. Yes. Yes, Virtual Protect. Virtual Protect is the actual Windows API that allow you to change memory permission. Usually when you write malware, you're going to need to do so. The truth is because you need to have a execute read-write memory location. By default, it's kind of hard to get an address of those, but because of the technique that I show you, you can actually get to the equivalent without ever calling this. And this is really the beauty of this technique is that you don't need to have such a call. So that's really what you want to avoid, and that's what we're doing right now. Yeah, usually one thing that is important when you compile your code, make sure that you don't compile it on your corporate environment because it's always going to have a bunch of strings that contain your username. So if you don't want to leak your company, make sure that you do either use a VN. You'll be surprised. Honestly, there's a bunch of rule sets that actually rely on that to detect malware. It's quite impressive because people forget about that. And same goes with the import table. When you have binaries that are compiled, I guess I can probably give you an example here. Let's pick whatever executable. Please all. Let's either load. I guess no, not the kernel. That's probably a terrible idea. Desktop. Let's pick that one. Doesn't really matter. When you compile a binary, I'm not going to go into too much details here, but when you actually have a Windows API like this one here, global alloc is a Windows API. Because I compiled that code on a specific system, the address may be different than yours or anyone else's computer. So to address that, it's fairly simple. The compiler, because when you compile, there's two things happening. You compile the code, which convert your C code into the assembly language that we see right now. And there's an extra step called linking, which allow the code to be run as an executable. And the linking process will actually create the import table, which is just a table that jump to a location. So in your code, every time you call these Windows API, let's say global alloc, and the code is just going to jump into that table. And at runtime, the OS will take care of mapping where actual global alloc is, and they kind of know. So regardless of the version of Windows, you'll be able to get your code running all over the place without any issue because of that import table. Pretty much the same concept applied to .NET in the sense that all of these methods like virtual protect, the deinvoke concept will actually leave artifacts that are well known. They know that if you have like multicast delegation, you're probably trying to do function pointer. And if you have assembly attribute type of thing next to it, or end invoke, begin invoke, they kind of know what you're doing in terms of structure because these specific functions and method leave artifacts that are known by security products. So as someone that want to actually create malware, you probably want to stay away from those. And this is exactly what we have here, in the sense that none of these are there. If you look at this piece of code here, is just a standard C# piece of code that fetch data from the web, which is fair. And this code here is fairly simple. The real dangerous part eventually will become that one, because they're going to understand that there's a lot of malware that start using it, because it's actually pretty clever and pretty neat in terms of detection. So this is the kind of stuff that you want to avoid. Yes, yes, yes. This one here, the byte pointer. Well, in the low level language, and low level has nothing to do with complexity. Low level mean that you're getting closer to the CPU and stuff like that. When you get to the low level, you have the concept of pointer. So everything in memory is pointing to a location. C# usually have a layer of abstraction on top of it that pretty much hide this from you. So all these methods are actually pointing to their location. But in this case here, I just wanted to have the raw pointer to that location. And the reason why is actually these language will tend to actually create clones and copies of the data for whatever reason. And when you work with the actual raw pointer, it probably saves your life, because you end up not having any kind of copy. Remember, at the end of the day, we want to have a shellcode running, and we want to make sure it's not going to be in memory at the end of the day. So we protect the memory to hide the shellcode. We use the concept that I just showed with the helper that allow you to prepare the method and do all of that, and then you are up and running, right? So you have to make sure that you work with the data to avoid as many copy as possible. That's why we ended up using the unsafe. Normally, you'll never write code like that, but in this case here, you want to make sure that you have the data where you want it, and you don't have extra copies that you didn't necessarily want it to see in memory. Well, you're going to have traces of your shellcode in memory, and this is something that you want to avoid, right? And you may not even realize it. I actually did a session not too long ago about that, where we write code that we see often online, and you realize that you have three copy of the actual string just because you use a specific method or function that ended up copying the code somewhere else, because the internal of the .NET core will actually ended up creating a clone because you're using a structure that just requires it. And as weird as it sounds, when you do memory allocation, when you copy stuff, usually it's going to be copied multiple times. So you want to stay away from it. So using the raw type like that prevent you from having extra clones and extra copy in memory. So back to this code here, we're pretty much done with the shellcode being placed in the proper location. So if you were to run this code here, obviously it's going to crash eventually. But back to what I was saying, now you actually need to get the shellcode running. Remember, we override the dummy function. So all we have to do now is simply call dummy, because the code now points to whatever you created, right? Normally, if we go back to what we are used to see, you'll have to create a function delegate pointer and ask, hey, please, can you actually jump to that location and pretend that it's code, which is another kind of red flag. In this case here, we're literally just calling C# again. So yeah, just call it dummy once more. Notice here that we call it just for fun, but it's going to work as expected because we didn't do any change yet. But when we're going to call it here, it's going to be a slightly different story. Now we have one more issue to address. At this point in time, we have the shellcode in clear memory, which makes sense. Eventually, you're going to have to execute it. But what we want to do is make sure that we are eventually going to get rid of that shellcode in memory. And this is where we're going to use the concept of working in parallel. So we're going to use thread to actually have two things happening at the exact same time. So we're going to have this new thread here. And in this thread, what we're going to do is kindly ask for the code to be clean. So we're going to create a new method. We're going to call this public static cleanup. Lack of a better idea here, to be honest. Um, and we're going to return void here because we don't care about the return type. And what we're going to do here is actually super simple. We're going to copy this and put it in here. The reason why it's in a different method is because we're going to use a thread. So we're going to make this work in parallel. And all you have to do here is call cleanup. and voila. And then T start. So you're going to actually start the thread in parallel. I'm just going to move dummy after, and you'll see why in a second. So the idea here is that you're going to create your thread. Your thread is going to do the cleanup, and in parallel, you're also going to run dummy. If you actually think ahead, you'll realize that there's a bit of an issue here. Start will run in parallel, so they may actually ended up doing two things at the same time. So unfortunately, if you protect it before you get to there, you're going to end up encrypting all that payload, and it's going to become an issue. And if you also think ahead too, you'll realize that we now have the shellcode in two different locations, right? We have the one in the shellcode variable, and we also have the one at that location here, which is the pointer to the location where we actually ended up creating it. So we have to do more than just unprotected. First thing, we're going to address the timing issue, and it's fairly simple. What we're going to do is going to sleep for a couple of milliseconds. In this case, let's sleep for 3 seconds. So this is going to start. It's going to wait 3 seconds, but this is also going to run in parallel, which is going to be more than enough time for dummy to do whatever they have to do. And now we're going to go back at protecting that memory location. Now the cool thing, if you look at protect, it expects an actual byte array of a location to actually protect. So what we can do is also do the same thing with the pointer location that we have in here. You could technically pass it as a parameter if you wanted to, because in this case here, address is not global to the function, but we could definitely add it here. So public in PTR, let's call it address, and let's just override this here. Here we go. Just need to find the reference to it. Program, blah, blah, blah. PTR, here we go. And now we can also take care of this one here, which is program address. We already have the address. The only thing that we need to do here is use this and ask kindly, hey, can you also please protect whatever it's that memory location here, which is going to be a byte array. Notice here that right now is an actual pointer. So you need to convert this into a byte pointer. And because it's a pointer, you can literally just do something like that, which is casting it to something that makes you happy. And now it's going to complain because it thinks that it's a bit too creative for its taste. So if you don't remember how to cast stuff, because I always forget, what you can do is hash the internet in PTR to byte C#, and it's going to tell you to do something crazy. You see, that's a good example here. If you were to copy this and use Marshall copy, what it actually do is ended up modifying the type. Marshall copy will end up creating a new copy in memory of the exact same code. So that's not something you do. In this case here, a better solution will be to literally re-implement this, and you'll see why in a second. Remember here, we were copying the shellcode. I'm just going to have to also make that available here. So let's create a static public API data and program data. Here we go. Now we just need to replace every places where we have data. I'm probably gonna forget one too, so it's gonna be fun. Here we go. I think I have all of them. Here we go. And I also need, yeah, I'm gonna need all of this here. Actually, let me just copy this. It's gonna save me a bit of time. Here you go. So now we need to remove that line because it's not relevant in this specific context. But now what we're going to do is we know that at this memory location, we used to have the shellcode. So it was overwritten each byte with something. In this case, what we're going to do is fairly simple. We're just going to specify a whatever bytes we want. Let's be creative. Why not just put CC? This is just hardware breakpoint. So we're going to protect the memory within the variable, and then we're going to go back to the dummy method and actually override it back with whatever. Another thing that you could do if you really wanted to, you can actually save all the bytes. Remember, you have a raw pointer to the method, so you can actually take those and revert it back to its original state, pretending like nothing ever happened. But point is, You have a thread that will start the cleanup. The cleanup will wait 3 seconds. While that 3 second is going, dummy will be called once more, which will end up running the shellcode. And then inside of this, you're going to actually take care of the memory with the shellcode, and then you're going to override the end with whatever you want. And we can definitely test that. I'm just going to save a bit of time. I'm not going to write the whole shellcode for you because it's going to be a bit time consuming. But let's take a calculator shellcode here. This is standard shellcode, nothing really fancy here. And we're gonna, oops, wrong one. We're gonna replace data here with the actual shellcode, which means that in this case here, instead of fetching evil string, it's gonna end up fetching real shellcode. Notice here that I kept data defined by redefining it with the shellcode. Evil string will just be gone. And if you actually run this in here, the program is just going to do its thing and trigger an access violation because I fucked up something somewhere. We just have to figure it out where it is. So unprotect is happening. Just want to make sure here. Let's troubleshoot this first. Let's try to see if it works that way. Stack Overflow. That's the beauty of doing it live. That's always the fun part. Trying to figure out where I made mistakes. Uh, do, 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 you know what I'll do? I'll just cheat a bit if you actually don't mind by just taking the original code that I use because of course when I do these live I actually have the code ready because it will be insane to just come up with this on the fly. So I'll just take the original one that probably doesn't have any mistakes. Oh no, that's not the right one. I probably don't even have it in here. Well. I know where it is. Visual Studio. Nope. Back. My loader. Here we go. So magically, we are looking at pretty much the same code. But I'll try to figure out what's the issue afterward, to be honest with you. But we are looking at about the same code here. And notice here that we have the same kind of thing. We're fetching. It's just that I'm using a slightly different endpoint. Let's just confirm that this one is still working. And as you can see here, it does its thing. Hello, I'm done. It finished. And as you can see here, a calculator pops, which means that you ended up executing your shellcode. But if we kind of look at the code, you'll notice that pretty much have the same structure. So we have the loop here, we have the star, we have the program dummy. It's probably what happened is probably with me doing all the variable renaming. I probably forget a address or something like that somewhere. One of these. So I just need to figure out which one is the one. But I guess, and by the way, just know that the code is going to be available later on. But yeah, so let's take a look at all the data and figure out if there's one missing programs and all of that. Another thing too that is kind of cool with .NET Visual Studio is that you can actually do debugging in a fairly cool way. It's well designed. So as you can see here, we have the pointer, we have the information about all the variables and all the information. So you can kind of inspect what's in there and see if there is any kind of issue. So in this case here, as you can see, we have program shellcode, we have the shellcode, we have all the bytes. So we can actually confirm that these are the proper one. By looking at it, that's it. It's probably kind of making sense. Then it's going to be decrypted by the unprotect. Let's just wait for this to disappear. Here we go, step over. So now, as you can see, the byte has changed because it actually ended up clearing the memory. So now the byte has changed and we're ready to actually copy this. And then you do, all the stuff. You copy the shellcode to the location forever, and then you end up in here. So what I'll do is just remove this. But I think we may have run into the issue that this is just not big enough, actually, because it's a memory allocation issue. So let me just add more to it. Because it ended up crashing in here. And how you can confirm that it's actually crashing here, my breakpoint is after the loop. And if it crashed inside of the loop, it means that something went wrong. So at some point in the loop, it was not capable of copying this. And it says attempt to read or write protected memory. So that's a good indicator that you are outside of the page, as we mentioned earlier. So usually making it slightly bigger does help, but it doesn't appear to fix it here. Trying to see if there's anything else that could cause that. The pointer is program address pointer. It's actually set to the proper thing, I'm assuming. So this is pointing to program address and PTR are the same, so that's good. You can always, what is it again? I always forget. That's kind of weird. Uh, in Visual Studio, you cannot kind of see the assembly for whatever reason on Windows 11. As you can see at the bottom, it's kind of blurred out. Not sure why, but normally you can actually inspect that location, but it does definitely point to the right location. But yeah, but something inside of that loop is like, nope, for whatever reason, eventually it's gonna crash. You can even see the counter, so I is at 4 and all of that. We can probably even put a breakpoint in here. So when it's gonna crash, if you look at the actual I value, yeah, apparently it crashed after 5, really? Step over, here we go. No, I'm not sure why the debugger was not showing the proper value, but that's the cool thing about debugging your code and doing it live. You always have to find out what happened, but eventually one of the offset will crash, and I'm pretty sure it's because we're outside of the page. But as I mentioned, making this big enough should actually solve your problem. But demo gods as usual. And funny enough, you know that it's working because I literally show you the exact same example that have the exact same result. But yeah, continue, show call stack. Anyway. So what we're gonna do is just flip back to this one if you guys don't mind. The only difference is that I'm only using shellcode here instead of having both as global variable. As I mentioned, I probably made a typo while renaming all the variables, so I ended up with improper offset because of that. But main takeaway here is you don't need to use none of the virtual protect and all of that to actually get your code executed. All you need is a bit of creativity. So you create a what appears to be a legitimate web endpoint. You write this in PHP or language of your choice. Just notice that you could also actually write it in C Sharp because even Linux support .NET for quite a while now. So you can have everything written in .NET if you wanted to. You can leverage the protect memory built-in class to actually hide your stuff in memory. Just make sure that you make it available before you do your little bad thing, and then convert it back to the clean state. And once the shellcode is run, well, everything has been cleaned up in memory and everybody is happy. And all of this is actually done with native C sharp code, which is always what you want to do. Keep your code as simple as possible. If you look at it from a malware perspective, the only part that actually does something suspicious is this method here, which is 3 line, which is fine by me. And you also have an extra couple of lines for the shellcode execution where you actually encrypt on it, move it to the shellcode location. But apart from that, that's pretty clean. It's not like you have 100 lines of complex code just to get to the shellcode execution. And as I mentioned in the talk, another thing that you can do if you consider this to be extremely suspicious, I love to use the concept of switch case. So what I'll do is have this while loop, and I'm going to create an index. So let's call it this. And the beauty is that you're going to use switch case. So the cool thing about switch case is that you can actually completely change the flow of an application by doing so. So what we're going to do here is that we know for a fact that we need to have these variables set. Because you're in a switch case context, though, you have to make them available outside of the switch case. So we're going to have the endl variable that is going to be here, and now we're just going to use whatever it's in there. What you're going to do is you're going to create cases within your switch case. And in this case here, you're going to have case, let's say 190, and then every case has to break. And let's create case, I don't know, 200 and break, and case 500 for and break. And then let's create case 600 and break. And what we're going to do is we're going to use this piece of code here. We're going to put it in the 500 case. And finally, we're going to put this one here in, I don't know, let's say, doesn't really matter really. In this case here, I'm just going to need to have the, here we go. So now we have this code running. The idea is that regardless of what you're going to do, you can actually make the code super ugly. Remember here we have the case of 600, for example, that doesn't really do anything interesting. Doesn't matter, we can have dead code. So if handles equals null, then set index to whatever, let's say 180. If it's not null, not sure what happened here. If it's not the case, yeah, there's a missing piece somewhere because it's messing with this. So we have a while, we have a switch case, break, break, break. Let me just add some break, case, break. 1, 2, 3. That should be good. Where is the typo? Unreachable code detected. Sure. Let's check the errors. Probably gonna help me. Cannot fall out of case 600. Sure. We can set a default if it makes you happy, but that's not the issue. There's literally just a curly bracket missing or something like that. Let's just play the figure it out game again. Expected semicolon. Where is it? What was that? That's right. Thank you for that. Yeah, I think it trying to autocomplete something for me. But yeah, there's definitely one missing something somewhere. Just need to figure out where it is. Um, Yeah, this one is open here and it technically closed here. The one for the while, this one is actually associated with the switch. But not sure why it complained about unassigned use of local variable. Yeah, because it doesn't know at this point if it's going to be used or not. But it should not complain about it because it's actually here. Let me just set this to null so it's going to stop complaining about this. This is super annoying. Why you cannot set this as null? One? No. What is expecting? I guess new runtime method handle, aka set to nothing. Doesn't really change anything. Now we have no complaint anymore. And back to making that code super ugly. So now we can have if index e is smaller than 0. Um, do something else, do the actual proper thing. So if it's smaller than 0, which we know that it's never going to happen because index is going to be set to 190, we can set handles. Yeah, I guess not a good example. We'll use index again and set it to 100. And this is the case where we're going to end up hitting index, but we know that this is the valid case. So we're going to set index to the proper real one that we want to reach, which is 500. So we're going to set it to 500. So we're going to exit that one. We're going to come back into the while and index will be set to 500. From there, we're going to eventually set it to the last one, which is 200. So you can create that kind of super ugly code. You can add more if you want to, like if, I don't know, index equals 190, do something. If it's not the case, do something. Just be extremely creative in making that code as ugly as possible. And here you can have index equals 0, whatever. And if you actually compile this, what I want to show you here is that I'm actually using which one now? My loader, right? Not sure why it disappeared, but here we are. So Windows, users, myself, source, Repro, my loader. If you actually look at the final result using a tool such as dnspy, which allow you to kind of decompile the code, you'll notice that all the switch cases that we actually ended up writing are gone. What had happened is that the compiler's like, hey, I can optimize your code to make it looks better, but it's actually as worse as it is. It's just that at the end of the day, it's going to look slightly different. So if you look at the program and you look at the get method address, remember, we ended up creating a bunch of switch case and it ended up being converted to that. The reason why it ended up doing this is the compiler realized that it can actually make sense out of all the condition that you had it, but it ended up creating a bunch of if else. The cool thing is it doesn't really matter what you use. I found that switch cases are simple to use because they're easy to automate in the sense that you can have a little script that take all your original code, in this case, the original 3 lines, and actually convert it into something that is extremely painful to watch. And if you have automation, you can even have more stuff in there, like while, I don't know, let's say current, smaller, whoops, no, index, smaller than 1,000, then index plus plus type of thing or whatever. So you just make the code uglier. It doesn't really matter what the state of index will be because once you get the end of that, case is going to be set to 200. So you make the application slower, you make the code larger, and you automate the whole process. So you can definitely avoid static detection. Back to, remember, let's say that EDR start to detect these 3 pieces of code as a pattern that is known to be malicious. By hiding that, well, every time you're going to recompile, it's going to look different. So it definitely help you with that detection. So back to what we had the web server that take care of hiding the shellcode, no encryption. What we did is just create some JSON object out of it, and then we actually pass that to the application. The application itself take care of converting this into an array. The array gets encrypted in memory until we use it. We retrieve the address of an actual .NET method. The address of that method is then later on used to be overwritten with the shellcode. Then we call back that method, and then later on we have the cleanup that actually work in parallel encrypt back the shellcode with the protect memory, and you have execution of your shellcode without calling virtual protect. You also have, everything that you need to evade static detection and runtime detection because you're not using much of the feature that we're used to see in that kind of context. And I guess that's it for me today in terms of live coding. I saw some of you typing on your computer. I don't know if you actually ended up writing the whole code on your side, but as mentioned, it's going to be available later on. And before we call it a day, I'm just going to take a look online to see if there is any kind of question. I've seen some interaction in Discord, so let me just check real quick. Yeah, okay, I can, yeah. What was the question? Yeah, sorry, I missed that one. Future Cowboy, probably someone asking a question earlier. But yeah, at the end of the day, that's one of the way that you can definitely evade detection with modern shell coding and modern EDR. So hopefully, you learned a thing or two today, and I'll see you next time. Yeah, it's always funny to go live. Let me just quit this. Uh, Especially when you modify your code live.